Just checking if you are able to hear my voice. If you can just say hi on the chat box, or just put thumbs up if you can hear my voice. Thank you. Alex, are you able to hear my voice? Is it clear enough? If you can just type something in the chat box. I'm just gonna quickly, if you can, just look this one. If you can just go on the settings and just ensure that you disable all the notifications, just to avoid the, if there's any pop-ups or notification that comes during the session. Thank you. What is that? Just checking if my voice is loud and clear. If you can just, yeah. Are you able to hear my voice?
Yeah, I can hear your voice.
Okay, perfect. All right, just checking.
Yeah, sure.
Okay. For everyone who just joined now, so on the screen, if you can just go on the settings and just disable all the notifications that might come up as we are trying to join the session.
So I need to uncheck here.
Yeah.
Okay, I did it.
Yeah.
I think this is.
Yeah.
It's gonna start in 20 minutes. Am I right?
Yes. Yes. Just gonna do a little introduction and then yeah. Hi everyone, thank you for joining us. My name is Barry, and today's topic for our webinar is footing design of industrial structures in LNG plants. This will be presented by our Dr. Bizat Mahabedzadeh, who is EIT lecturer and senior structural engineer. Yeah, just note that copy of this slides and the recording will be shared with you upon completion of this session. Just expect it within 1 to 2 working days. This will be sent to your emails. Just also check under junk. Sometimes the email doesn't go straight into the inbox. And then also, we do provide a free digital certification of attendance. So yeah, we will be sending you a link, or I'll share the QR code upon completion of the session, which will lead you to more like a survey in order to receive your certificate. For those who just joined us for the first time, just to give you a little, overview about EIT. Yeah, so when you think of EIT, think of engineering. We are the engineering specialists. Our main focus is just providing engineering programs. Our program starts from professional development programs all the way to Doctor of Engineering that include the likes of our advanced diplomas, our bachelor's degree, our undergraduate, master's, and so forth. And just as you may know that, technology is changing, job market is changing, and at EIT, we are industry orientated, ensuring that we keep up with the trends, we keep up with the changes. So we ensure that our material and our technologies are up to date rather, to ensure that we keep up with the trend, and also our students receive relevant education. Just to touch base more on the accreditation, our vocational programs and higher education courses are accredited with Australian government, just like any other education provider in Australia. And then we also do have some of the programs that are also recognized under 3 international engineering accords. We have our advanced diplomas that you find under Dublin Accords. We've got our bachelor's programs that you find under our Sydney Accords, and also our master's programs that are under Washington Accords. And then just also to touch base on what really makes EIT unique in terms of industry experience lectures is that we source our lectures from different parts of the globe, just to ensure that our student gets relevant education and quality education as well. And in terms of delivering our courses, we do have a unique methodology that make use of our delivery by use of live and interactive webinars. And like I mentioned, that we have a pool of experts that they actually instruct our students. Yeah, so for those who just joined, if you can just go on the setting and just disable all the notifications to ensure that you don't get any disturbance.
Importance level of the importance level of the region that we are going to design this structure for is importance level 2. Also, this shows the importance of the structure because it's an industrial building, so it is not that much of importance because no one or less people during the service is in danger. Probability of accidents is 1 over 500. Probability factor is Kp equals to 1. Soil class B hazard factor is 0.1. Spectral shape factor is 3.5, and ductility and performance factor S sub P over mu is 0.38. Here the tables that you can find in the standards, and here at the left side, you can see the importance level. Here, importance level. And we already know that the importance level is 2, so we can have the wind load and earthquake loads. And this is the annual probability of accidents, or APE. As you can see here, is 1 in 500 years. And how we get the importance level, you can see here, this importance level of buildings or structures not included in importance level 1, 3, or 4. So we can go to the level 1, buildings or structures presenting a low degree of hazard to life. So the most important part is the life of the people. And other property in the case of failure. And 3, buildings or structures that are designed to contain a large number of people, for example, high-rise buildings or any commercial building, as well as the buildings or structures that are essential to post-disaster recovery or associated with hazard facility. For example, the fire stations and hospitals. So our building or our structure, which is the plant, is not categorized in group 1, 3, and 4, so the importance level is 2. Here, from this table, we can find out the hazard based on the site soil class. We have the soil class B here, importance level 2, and also the structure height here is lower than 12, so the KPZ would be something lower than 0.11. This is the earthquake design categories, and this is how we can find the hazard factor. And here also this table also helps to find the base shear coefficients based on the characteristics of the structure. Here we have the building type, spatial shape, or this is the period, and this is the ductility performance, and this is the formula for base shear, ductility and performance SP over MU for this type of the concentrically braced steel frame, light roof, and concrete or concrete slab. Here we have the concrete slab. So this ductility and performance would be 0.38. And the other coefficients here. And this is also would be the base shear. So here, based on the equation, we have the base shear calculations. We already get to know about the parameters that we need to put here. At this slide, we have all the parameters that we do need. Then thus substituting in this equation, we can find out the final equation for the base shear with respect to the weight of the structure. And we also need to consider that this weight of the structure is the in-service weight, because this is the LNG plant. The majority of the structures are prefabricated and just shipped to the location and installed on the footing. So we should know that for the earthquake design, we need to consider kind of the operation weight or wet weight. But for the wind design, we need to consider the dry weight or shipping weight. And this is because in the earthquake, the base shear, as you can see here, is a direct function of the weight of the structure, and it affects the earthquake loads. Anyhow, for the wind design, the weight of the structure helps to resist the wind load, so we need to consider the dry weight of the structure, not the in service. Here you can see an illustration of this Amine treater. It could be the general shape would be like this, and we use this to go and do the design. The illustrative dimension of this structure is 16.2 meter in length, width of 4.3, and also the height of 4.1. Structural weight, as we already learned, that we need to use two different weight. One is the dry weight or shipping weight, and another one in service or operation weight, including the liquids or any live load or any other dead load. So for this structure, we consider the 29.615 tons as the dry weight, which equals to 296.2 kilonewton. Disregard this, and the operation weight would be 41 point almost 18 and equals to 411 kilonewton. Now we need to consider the load combinations. So for the ultimate load combination, the first one is 1.2 G plus 1.2 Q. Here is the self-weight of the structure, and this is the vertical operation load. And the second combo, we each the self-weight of the structure plus the earthquake loads, which is considered as a base shear, and then the resulting moment. And the last one, load combination 3, is 0.9 G plus W. W is the wind load, and here G is the self-weight of the structure plus, the vertical, the dry load, shipping weight. The first step to kind of solving this problem or doing the design is a simplification of this structure. We do have something like this. This is the length and dimension of this structure, and these are different parts of the columns and also containers. Here at the left side, you can see here the 3D view, and here is the view in this direction, length of the structure, and here is this one is in this direction. Footing design based on for the earthquake structure, earthquake loads using the structural toolkit. For this structure, we consider 12 independent footings each side. So if this is the structure, we have some footing like this. Structure, we have some footing like this. So there are 12 of this, 6 at each side. The design is done for the middle footings that takes the biggest portion of the load. You know that if we consider this one here, if we have one footing here and one footing here and one here, the half of this and half of this would, and also one here, would be transferred to this. So this is the tributary area of each footing. The footing is designed considering the 85% of the operation weight concentrated on the part on which the containers are placed. Here are the containers. So we need to design for this part, and we can see that the 85% of the loads would be applied on these two footings. So we design, so it is a kind of conservative design, and then we can generalize this footing for other parts, or we can do the design for the rest. It depends on the engineer's decision. Here you can see illustration of this structure, Amine treater. You can see 1, 2, 3, 4, 5, 6 footing at each side, and this is the longitudinal direction, and here is the transverse direction. So totally we have 12 of the footings, and here you can see the tributary area that considers 85% of the operation load applied to this part. So the portion we are going to design for this middle footings. So this blue one is a tributary area for these two footings. We already calculated the base shear, or the force of the earthquake is 0.13 multiplied by the weight of the structure. Here we are going to design for these two footings, so we need to consider the tributary area for that footing. The total weight is about 411.8 kilonewton, and the tributary area would be here, this part. As you can see, let me clean it up. You can see here is 3,240 mil, so it's gonna be 6,480 multiplied by here this width 4,300. So this would be the total tributary area that these 6 footings going to support. And load per tribute, and the footing design load, we already considered 85% of the total weight of the structure to apply at that location. So 350 kilonewton is the load applied on this tributary area. Then just dividing this load by the tributary area, we have this as the load per unit of the tributary area unit, or unit of the tributary area. Then we need to consider the area for midfoot. From here, just to illustrate, from this part to this part, this length is 3,240. So the 3,240 multiplied by 4,300 mil, this would be the area that the middle footings support. Then load per 2 mid footings is the multiplication of this coefficient, or the load per unit area of the unit area of the tributary area multiplied by the area gives us the load for 2 footings. and we have 2 footings, so just divide by 2. This is the load that each footing needs to support, 87.5. We have 3 load combinations. Combo 1 is 1.2 multiplied by 87.5 gives us 105 kilonewton. Combo 2 is the earthquake load or seismic load, 0.13 multiplied by the load per footing, load of the tributary area. So we have 85.7. So this is the base shear. Also, we need to consider the center of the mass is the height of the structure is 4.1. The center of the mass would be at the center, considering the here. If we consider the initial at the initial stage, we consider the total depth of this footing is 0.8 meter, and here is the height is 4.1. Considering the middle, so this is the arm for the base shear or center of the mass is 4.1, which is over 2, which is 205 plus 0.8 is 2.85 meter. Now we need to calculate the moment due to this base shear that applies here at this part, kind of overturning moment. 11.38 multiplied by 285 gives us 32.43 kilonewton meter. Gives us 32.43 kilonewton meter. And based on the standards, the Vy or the base shear at the perpendicular direction to the main direction is 1/10 of this base shear. Here we have the base shear 11.38 and 1/10 would be almost 1.14 kilonewton. And the moment due to this shear would be the multiplication of this base shear at the perpendicular to the main direction by the arm or center of the mass, which is 3.25 kilonewton meter. And we need to consider that these two actions work together. Now we need to estimate the footing dimensions. In order to design and find out the dimension of the footing, considering the seismic loads, we have used the structural toolkit. And also we need to consider, because we are going to design the precast footing, there is a concern of the lifting of this footing. So we consider 2.5 ton as the criteria for the weight of the footing. Here is the structural toolkit. We just need to give dimension here, and here is the applied vertical load, and these are the moment due to the base shear. And here is in the opposite direction. Just disregard this. So the dimension of the this is considered. So these are the input that you need to have in the structural toolkit, and this is automatically calculated based on this amount that you put. So for now, these are not the input that you need to provide. Only this circles one. And based on this load and considering the load, because we already applied the ultimate load factor, so we don't need to go for the LL. If we go for the LL, which is the live load, we have 1.5 factor, the factor of 1.5, which make the design conservative, or we have over design, which is not of desire. So based on this numerical values, we have the width of the footing 1.85 meter or 1,850 millimeter. The depth is 750. Also here you need to provide the lower bearing capacity of the soil. Here, based on the width of the footing, and also geotechnical report, you need to refer to a geotechnical report that provides you with the load bearing capacity of that area. So you need to input here, and sulfate density of the concrete is 25 kilonewton per cubic meter. And also we consider the elastic. We want the footing acts in elastic range. Here, because the Q here is the live load, here we don't have the live load. So because of that, we only consider the 1.2 G. Footing weight. So we already knew that we have the criteria of 2.5 ton for each segment that we need to ship to the location. So the total footing weight is 1.85 by 1.85 by 75, and here is the weight of the footing concrete in kilonewton per cubic meter. So we have the 6.55 ton is the weight of the footing, which is not of desire because of the shipping. Not okay. We need to use the pedestal system by considering 3 segments through the footing depths. It means that we consider like this. If this is the independent footing, in order to have the segments portable, we have 3 segments. We make this footing that we need to have this footing 1.85 1.85 by 75.75, but we also have this criteria, so we need to have 3 segments. So this is the pedestal system, which is the 1850 by 1850 multiplied by the thickness or depth of the each segment is 250 here. So the weight of the footing is 2.18 ton. So it is lower than 2.5. So it is okay, and we meet the criteria. Now we need to go for the wind design. For the wind design, we use the AS 11.7.2. Based on this, we have the wind load as the 1.22A. For the wind analysis, the shipping weight, as we already mentioned, is considered. Footing design load, this is the shipping weight or dry weight, multiplied by 80.85 for the middle footing is 251.77 kilonewton. And load per 3v3 area, just dividing this load per by the 3v3 area gives us this number. Here shown the footing that we need to design for the wind for the tributary area. The dimension that the wind acts is in a vertical direction. So we have one here and one here, and also if we see from the side, this is the wall, and we have something like this that on which the wind acts. A is the 3240 multiplied by the height of the structure. Here it should be 1. This the height of the structure is 1. We have the area load per 2 mid footings. Here, this is the load per tributary area, and excuse me, this is the area of the tributary area. This is true. We want to find out the load per tributary area because it used in the design. So this is the tributary area here, and load per tributary area, just multiplication of the load per unit of area, and the tributary area gives us 125.9 kilonewton. We have 2 footing, so the vertical load here is 62.95, but for the earthquake load, which we consider the operation weight was 87.5 kilonewton. Now we need to calculate the wind actions. If you remember in the first, at the early of this webinar, the illustration of the Amine treater, it is not a complete box. So it means that we don't have walls here, but we have some equipment. So to not to go for the over design, also to be in the safe design, we consider the 80% of this area as the area that gets the wind. So wind load is calculated based on the 80% of this area and this area. So 3.24 here, this direction, multiplied by the height, which is 4.1, gives us 10.63 square meter. And we already calculated the wind load for this area is the factored 1.22 multiplied by A gives us 13 kilonewton. So we have 2 footings. So each load is distributed on each footing for this tributary area. So 13 over 2 is 6.5. And we already calculated center of the mass, multiplication of the P here, the lateral load by the center of the mass. So we have this moment at the lower part, or overturning moment, which is 18.53 kilonewton meter. Then in the perpendicular direction, in this direction here, we have 4.3, which is the width of the structure, multiplied by 4.1, which is the height of the structure, multiplied by 0.8, gives us 14.1 square meter, multiplied by 1.22, gives us 17.2 kilonewton. And we have 12 footing, where if the wind acts in this direction, here, all the load is taken by these 12 footings here. So we divide this load by 12. We have the 144 kilonewton. This is the load that each footing gets if the wind blow in this direction. So the moment due to this lateral load is 4.1 kilonewton meter. And also the structural toolkit is used to do the design. So as we already did for the earthquake design, we put the here is the vertical load that we already calculated, and this is the moment 18.5 that we already calculated, and this is the horizontal or lateral load or shear. So this is the here this is the auto calculated by structural toolkit, and the important part that you can see or the substantial difference between the earthquake design and wind design is that for the earthquake we have the x and y direction, or main and the perpendicular to the main direction, but we need to put the both because when the earthquake happens we have the shear forces or seismic loads at both directions. But for in the case of the wind, we only have the wind in one direction. We don't have the wind blowing in two directions. So we need to consider the most significant one. And based on this data that we provided here, we have the design width is 900, length 900, and the depth is 750. And referring to the geotechnical report, and with respect to the size of the footing, we have this load-bearing capacity of the soil. So so far, earthquake is dominant. For sure, we already also knew that for short structures, the earthquake is dominant. But when we go in height and for the high-rise structures, wind is dominant. And we can practically see this sort of things here. So we need to do the design for the earthquake, and it would because it is the dominant. Here we have the dimension of the footing that we already calculated for the earthquake. So we have the section. We consider for the space gas modeling, we consider this section. Here is 1.85 meter, and this is the depth of the footing, which is 0.75. We already also calculated, so just for your simplicity to just illustrate, we also provided here the vertical load is 87.5 kilonewton, and we have two-way. So this slab, as you can see here, this is the section. Here is section. Just I write here SE, and this is the plan view. Okay. So the vertical load applies here. This dimension equals to this dimension. Am I right? Here is 1.85 dimension equals to this dimension. Am I right? Here is 1.85, 1.85. Let me write down here for simplicity or convenience. 1.85, 1.85. So because it is the we have the criteria for the footing that when L over B is lower than 2, we have the one way. If it is greater than 2, it is one-way slab. It means that the load applied on the footing just transfer in the shorter direction. But here we have L over B smaller than 2, so we have the two-way. It means that the load transfer in this direction as well as in this direction. For the sake, so because it is a two-way slab, we need to consider this 62.95, which is the vertical load applied on this footing, over 2. Why? Because it is two-way slab. So this is the load that you need to consider in the analysis of your footing in the space gas. For sure, we have 3 load combination as we have here. And this is the model made in a space gas. This is the combo 1.2 multiplied by here the load that we already calculated, 31.48 applied on this, and this dimension is 1.85. And in the space gas you can just select this element and make a section for that. So the section is something like this we already showed. And combo 2, we have 2 direction. This is the earthquake. So in the longitudinal direction we have the vertical direction, vertical load 43.75, and this is the moment applied on the footing, 32.43. And also we need to consider the spring here. You need to provide, based on the geotechnical report, you need to provide the stiffness of the spring. So this is the soil here, soil. So you need to apply the spring stiffness. And this is transverse direction. You can see the vertical load is the same because it's the two-way slab, but this is the moment, 32.43. Here the moment is 3.25, but 1/10 of the main direction. And this is for the wind load. We have also here doing the analysis for the longitudinal direction, and here is the transverse direction. And these are, after doing the analysis, these are the reactions. For the combo 1, the bending moment looks like this, and this would be for the combo 2, longitudinal direction. The moment is like this. This is the maximum moment that the slab needs to, or footing needs to sustain in the longitudinal direction. And here for the earthquake loads, earthquake, and here is in transverse direction. And here the wind load, combo 3, here this is the reaction in the footing. So the moment is 34.82, 27.6 kilonewton meter, the maximum. And another reaction that we need to look into is the shear forces. You can see the variation and distribution of the shear force into the footing for the load combination 1. And here is for a load combination 2. And this is for the load combination 3, which is the wind load. Taking into account the moment and shear forces, we need to check the footing. We already designed the footing, and now we analyze the footing. We have the reactions. Now we need to check it. We use the 40 megapascal concrete, and the dimensions are this. We consider the 50 mil cover. It means that if this is the footing, here these are the rebar, and this is the cover. And now we need to do the shear check. Shear check. AS based on the concrete standard, AS 3600 2018. VU, the total capacity, shear capacity of the section is the VUC plus VUS. C refers to the concrete, S refers to the steel. VUC, the shear capacity of the concrete, can be obtained by this equation, KV, BV, DV, square root of the compressive strength of the concrete FC, which is 40 megapascal. And these are the equations based on the standard that we can use. Because this is the footing and we don't use the shear reinforcement, we don't consider shear reinforcement in the footing. So we need to go for this equation. Epsilon is the strain. Here, KDG for the aggregates greater than the here 16 or 20 mil, KDG is 1. So we consider this criteria and we consider it as 1. And this equation can be used for the KDG 32 6/16 plus DG, and DG is the maximum nominal aggregate size. Anyhow, we consider KDG as 1 because we consider DG greater than 16. So DV, based on the standard, this is the effective depth for the shear, is 0.72 multiplied by the depth of the footing, and this is the 0.9 multiplied by lower letter D, which is the effective depth. What is the effective depth? This is the total depth of the footing, D, which is 0.75. This is the total depth of the footing, D, which is 0.75. And considering the rebar here, which we consider to be N10, here is 50 at the center line of the rebar. This would be the effective depth of the section, D small. This is D. So dV, the effective shear depth, is the greater of these two. We consider double reinforcement here. So 750 minus cover minus 10, the diameter of each set of the rebar, because if this is the plan here, it is a net. Just consider at the bottom part, this is the bottom reinforcement and this is the net here. So one is below, one is upper, as we can see here. So 75, 750 millimeter minus 50 minus 10 minus 5, because this one is at the center line of this rebar. So the effective depth of this section is 685 multiplied by 0.9 is 616.5 mil, and 70.2 D is 540. So the greater of this, so the effective shear depth is the 616.5 mil. And here are the equations that you need to calculate the strain. M star the applied moment. This is the reaction that you get from the analysis in the space gas. You need to pick the maximum one. dV, we already calculated dV 616.5 with the shear. This is the reaction also you get from the space gas. 2 EL, this is the elastic modulus of a steel, and this is the area of a steel. And using this equation, we can find out by solving the quadratic equation. You can find Q, and here Q is AST. You can find out AST multiplied by Fy, which is the yield strength of the steel, over BD, which are the B is the width of the footing, the effective depth, and FC is the compressive strength. Just substituting the amount, you have the AST for the required steel area for this moment and this section. Just put or substitute in this equation, the epsilon would be 0.0015. Having the KDG 1, you can calculate the KV. So just substituting the amount into this equation, you will have the KV. Now you can calculate the factored shear capacity of the concrete. 0.6 is the factor that you consider for the shear capacity, multiplied by 0.099, which is kV. BV is one. This is the width of the footing, 1.85 meter, or in millimeter we just write down 1,850. This is the DV. Here, DV. It should be 616.5. Here, this is DV, 6.5 millimeter, multiplied by the square root of 40. You have almost 430 kilonewton. This would be the factored shear capacity of the concrete. Then you need to calculate the flexural reinforcement based on the moment that the section needs to sustain. Here, back to the reactions. Here you can see the maximum bending here is 550.26 kilonewton meter. So just using this amount and using this equation, we can find out the required amount of the steel. We can use N10 at 300 spacing. Anyhow, this is the things that you can find from the here, but from the experience, you'd better to use N10, maybe at 180 or 200. It is suggested to be, but based on this equation, we can have this. This is flexural reinforcement, or in order to be in the safe design, you can use N12. Anyhow, for now, based on this moment and this area of steel, just wanted to go with these equations and make them happen. So we have N10 at the 300 mil spacing. So do you remember that we have this criteria 2.5 ton? So we had to divide each footing in 3 parts because this is the prefabricated footing in order to make them portable or lift them and transport them to the location. So we need to connect these 3 parts together. So how we can do this? Using the shear connectors. In order to design for the shear connectors, this is the V, shear stress, this the applied shear force, Q, the first moment of section or sectional moment, first moment. And this is the second moment of inertia. B is the width. QC can find out using A multiplied by C. A is the area that this is the area in the plan here, this area. This is the area in the plan here, this area. And based on the characteristic of the section, here is the depth, D, and here is the width. We have this I. T is the thickness of each section, 250. B is the width here, this one, B. And the here area, B multiplied by T. C consider the spacing here, 300. And QC here is A multiplied by C. And V star, we already got this from the reactions in Newton. And just using this equation, we can find this. This is W, this is L. So multiplication of the W and L is the area, and multiplied by shear stress, we have this shear force that need to be supported by this shear connector or resisted by shear connectors. Here we use N16. The area of the N16 is 200. Phi V is 0.8, 0.6, 200. This is the yield strength, Fy. So the Phi V provided, this is the shear force that or shear resistance of the rebar. The number of these shear connectors can be easily found by the dividing this shear force calculated here over the shear resistance of this rebar. So we have 6 and 16 each direction. It means that we need to have 12 and 16 shear connector. And also we need to have the 4 and 16 anchors. So if we have something like this, each direction 6, then I will show you how to distribute this, and at the middle 4 down anchors. If this is the section, they are like this. These are the down anchors. And here you can see the illustration of this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we can distribute these 12 anchors into the footing to connect them. Here is this. This is the depth and this is the width. You can see the shear connectors are like this. And this helps to connect these 3 parts together to work as a one footing, because we have 3 segments, prefabricated segment, that we need to connect them. Also, you can see here, this is the here down anchors that are shown here. And this is the flexural reinforcement. Also, we can use the SL81 here, as you can see here, SL81 mesh. This is for the down part here, bottom part, but at the other parts, due to the lifting, we might have some deflection. So also due to some small negative moment, we would better to have the mesh here in order to prevent any crack in this prefabricated footing. Anyhow, we have also other recommendation. If the depth of each segment is greater than 150, which is here 250, we would better to have N12 here or N10 rebar for each segment instead of the only here have the SL81 mesh. Anyhow, this one also works. And this is the end of this webinar, footing design. Thank you so much for your attendance. I hope that you enjoy the class, and I hope that I could help you to have a general understanding of the footing design for the industrial buildings. Any question regarding this lecture topic, I would be super happy to help you.
All right. Thank you, Bizat. Great session. Thank you for everyone for taking part in this webinar. Just to highlight some of our upcoming courses. As you can see here, we've got our micro-credential program, the professional certificate of competency that they actually run throughout the year. And then we also have our diplomas and advanced diplomas that you can also join throughout the year. We have our undergraduate certificates together with the bachelor's programs that are taking place in July the 24th. And then our graduate certificates on the 26th together with the Master of Engineering degrees programs. And then our Doctor of Engineering will be taking place on the 24th of July as well. And then our on-campus programs, including bachelor's, master's, Doctor of Engineering will be taking place on the 31st of July. You can just click on the link or just go to our website, eit.ag.au, just to view our schedule. And just to add more on our upcoming webinars, we've got the importance of incident investigation in the workplace. The webinar will be taking place on Thursday, the 23rd of March. And then we also have effects of harmonics and on distribution transformer efficiency, which will be taking place on the Thursday, the 16th. And yeah, so you can always just go to our website under news and events in order to be able to sign up for the upcoming webinars. Yes, I think a few of you might have been asking about the certificate of attendance. So usually what you can quickly do, you can just take your phone and scan the QR code. I will also just copy this link and just put it on the chat box. Yeah, so you can just scan the QR code, or if you can just follow that link. There's a form that you will need, a short survey form that you will need to complete. Then that will lead you to obtain your certificate of attendance. I'll just leave this one for now. And then just note that the certificate of attendance will be sent to you within 1 to 2 work days. All right. Yeah, so I don't know, is there anyone who's got a question to our lecture? I think we've got a Q&A session that we can have.
Yes, if any question, I would be super happy to help.
Hi, Debza. You will be getting an email within 1 to 2 working days with the slides and copy of the recording. So yeah, just check your emails. Just also check under junk or spam folder. Thank you. Okay. So just for further details, if you've got any query that is something that you need to know, you can always just send us an email. You can go to our website or you can give us a call. These are our contact details. I'm just going to go back to the slide for anyone if you want to scan the QR code. And one more time, I'll just post the link again. If you're unable to scan the QR code, you can alternatively just go into the link. Hi, Bizat.
Yes.
We seem to be having a question coming from Brian. Brian says, I beg your pardon on why operations weight is considered in earthquake and dry weight in wind design.
Sure. Thanks for your question, Brian. For the earthquake design, the shear for we know that the weight of the structure is the factor that affect the seismic loads. So it means that we need to consider the higher weights. So why higher weight? Because we consider that this structure prone to the earthquake when it is in operation. So we need to consider the higher load in order to go in the safe side. For the wind design, you just consider or just consider two persons. One has a 60 kilogram weight and another one 90 kilogram weight. So which one is more prone to overturning when a wind blows? The heavier or the lighter one? For sure, the lighter one is more prone to the movement, to overturning or something like this. So in order to go for the safe side, because the vertical load is the helping load against the lateral load in the terms of the overturning that we already considered. Here is the footing. Here we have the lateral load. Here we have the arm, and overturning would be somewhere like this. We have this vertical load here. It helps to act against, so this moment acts in this direction, this moment acts in this direction to help, this overturning moment. So it helps to resist against this lateral load for the overturning. So in the case of the having wind, we need to consider the lighter weight, which is the dry weight or shipping weight. But for the earthquake, the heavier weight means the higher loads. So we need to consider the operation weight. I hope it helps. Is it clear, Brian?
Yeah, Brian says yes, it is very clear.
Okay. Yeah, sure. Thank you for your question.
There's another one. Is it Wakamuna? Why operational in earthquake come again?
Because it acts on the foundation. We have, the lateral load when earthquake happens, the lateral load is the proportional of the some coefficient that I already explained, that how we get to know about those coefficients to get, for example, here we have the base shear or the horizontal load as a factor of the here W. Okay, this is the lateral load that is a function of the weight of the structure. It applies in this direction. Anyhow, considering this footing, we still have the weight of the structure that we need to consider here. So we cannot, this is the horizontal load due to the earthquake applied on the structure. Anyhow, we have also the weight of the structure that we need to consider. So because of that, we consider this operational load. Because you have the weight on the footing. Just consider a building. It has its weights, but the earthquake loads is a proportion of the weight of the structure applied horizontally, and we have also vertical load of the structure that applied on the footing. So this vertical load also should be sustained by the size of by the footing. Because of that, we need to consider the soil load bearing capacity. Going to geotechnical report and find out the soil loading bearing capacity. If your dimension doesn't work, it means that it cannot bear. So you will have uplift. So you need to increase, if it doesn't work, you need to increase the dimension of the footing to provide enough soil load bearing capacity. It means that you distribute the load in the wider area, decrease the stress so that the load bearing capacity exceeds the applied stress. In that case, we don't have uplift. Any other question? It's not called, sorry for that. It's not called the shipping. It is a dry load, but because we're talking about the prefabricated, the dry load is the load that is the structure that can be shipped. So it is not the shipping load. Just in this case, because they are shipped, we call it shipping load, but it is not a shipping load. Anyhow, when you want to ship this, so you need to consider this load, the dry load, because it is not in service. No worries, you come on now. Any other question?
There's another question here coming from Brian. He says, briefly explain steps in carrying out earthquake design for footing, please.
Brian are already at the early stage of this webinar explained how to conduct the earthquake design. You just need to go to the here. You need to first find out the array of the footings and how many footings. Here you need to find out the weight that each footing needs to take. Then based on the equations here that we already found using the tables in the standards here, we already explained about these tables. The importance level, the importance is given here, and also the APE, which is the annual probability of exceedance. We can find out these coefficients from the geotechnique, and also you can find out the soil class and this sort of things. Then just using this equation, substituting the amount, you can find out the base shear or the lateral load. And this illustration of the building, and then just structural weight, load combinations, and then go for the earthquake design, considering 12 independent footing and the tributary area based on the configuration of the structure. Find out the load each footing needs to take here, as we already explained here. The load for each footing is 87.5. Then 87.5 multiplied by 0.13 gives you the in the main direction, the lateral load in the main direction, and in the perpendicular to the main direction based on the standard is 1/10. So this one. Then go to the structural toolkit, put the amounts here for the main. Here is for the main direction, and here is for the perpendicular to the main direction or minor direction. You can find out the footing dimension. So I think there is another question. Mustafa Siraj, we already explained why the operation weight is used for the earthquake, because the as I just already mentioned, the earthquake load is a proportion of the weight of the structure. So in order to earn the safe design, and because it is in service, we need to consider the operational load. But for the wind, we need to consider the dry, because the lower means the lower weight means that the more conservative design. Any other question, guys? So solving a problem using Eurocode. Sure, I would be happy to do that next time. Any other question? Barry, I think there is no more question. I will hand over the session to you to wrap it up and over the day.
All right. Okay. Yeah. First thing first. Thank you so much, Bizat, for facilitating the session. We really appreciate, and thanks to everyone who attended the session for today. Yeah. So in terms of the recording and also the slides, you will be receiving an email within 1 to 2 working days. So just also check under junk or spam folder. And then once again, for those who were asking about certification of attendance, I will just quickly go back to that slide again. So if you can just see if you can just scan the QR code, or for the last time, I will just share the link for those who cannot be able to scan the QR code. Yes, this is the page. So just note that your certification should be sent to you within a period of 1 to 2 working days. So if you can take some time and scan the QR code, or alternatively, you can just go into the link. All right, I think that's it from me, and thank you, everyone. Have a great day.
Thanks everyone. Thanks Barry for your kind efforts. Have a good time. See you next time, guys.
Yeah, definitely. Thanks.
Thanks. Bye.